try it again. Okay, review here. Blood vessels, arteries, capillaries, and veins. General principles of. On the graffiti right here, we have a illustration trying to show a comparison between three different types of arteries, three different types of capillaries, and three designations of veins. We'll start off with the idea that on the side right here, I have a squiggly line representing a variation in blood pressure. In the arteries closest to the heart, there is a pulse, but this pulse diminishes and disappears in the area of what's called the arterioles before it reaches the capillaries and then continues on in the venules, the veins, and the Vena Cava. So the pulse is only located in the larger arteries. It's not found in the arterial capillaries, venules, veins, or Vena Cava. Significance. One reason why that's significant is if we look at a quick comparison between an artery and a vein of the same outside diameter. First off, when it comes around to the size of the lumen, the arteries tend to have a smaller lumen. The veins tend to have a larger lumen. When it comes to the thickness of the wall, the arteries tend to have a thicker wall. Veins tend to have a thinner wall. When we look at the pressures inside, arteries tend to have higher pressure. Veins tend to have lower pressure. The artery may have a pulse inside. The veins do not have a pulse inside. And generally speaking, the velocity of the blood is higher inside the arteries and it's lower inside the veins. The thickest part of the wall of an artery is something called the tunica media. And it's this spot right here that may contain smooth muscle and elastic fibers. For the vein, usually the thickest part is something called the tunica externa. And the tunica externa is made of areolar tissue. Real quickly, here's a comparison between those three possible layers. The innermost layer of any blood vessel is called an endothelium, and it's made of simple squamous epithelium. Now, that being said, the three layers of an ordinary blood vessel are considered to be the tunica interna, which was the endothelium, then something called the tunica media, and then the tunica externa. Of course, we very often have two names for the same thing. So the tunica interna is also known as the tunica intima, because by this name right here, it is intimate or close to the blood. The tunica media is just that, the thing in the middle. And the tunica externa is also known as the adventitia, which implies it's to the outside, as does externa. As far as the tunica interna is concerned, also known as tunica intima, also the endothelium, also known as simple squamous epithelium. It is simple squamous epithelium, so therefore a single layer of flattened cells, the thinnest possible barrier between the blood and the things behind it. Again, the endothelium is continuous from arteries to capillaries and veins in most situations. Now, in the larger blood vessels, the endothelium may have what's called a subendothelial layer, and it is made of areolar tissue. This is the area immediately below the basement membrane of this simple squamous epithelium. The significance is, because it's made of areolar tissue, there's a possibility of fat being deposited inside that area right there. And if fat is deposited inside that area, the volume of the fat won't push the outside wall out. It's more likely to push the endothelium in towards the lumen, and thus create an occlusion. So when it comes to fat being deposited inside the wall of a blood vessel, very often the subendothelial layer is where that occurs. The tunica media, again, is made up of smooth muscle and elastic fiber. The amount depends on which vessel you're looking at, and generally speaking, how close it is to the heart. The tunica externa, also known as the tunica adventitia, again, is areolar tissue and acts like a Velcro material, sticking the blood vessel to some neighboring structure. Thus, blood vessels very often look like vines clinging to a surface and creeping along, such. Looking up here at the designation of the different types, the arteries that are closest to the heart are called elastic or conducting arteries. Elastic refers to the makeup of the tunica media, and conducting refers to the function of these. The most obvious example of an elastic or conducting artery is the aorta. And the main purpose of the aorta is to get the blood away from the heart as quickly as possible so that the next surge of blood on the next cardiac cycle doesn't run into the back of the first surge of blood. Well, this is the general way in which it's accomplished. There is a lot of elastic fiber inside the tunica media of the aorta. When the stroke volume from the left ventricle enters the aorta will bulge outward. As it bulges outward, it absorbs the energy from that surge, from that pulse right there. So the systolic pressure, much of the energy is absorbed into the wall of the aorta. Then when the ventricle relaxes and the stroke volume drops, the pressure drops, the aorta will return the energy that it absorbed from that first surge. So it acts like a kind of a rubber tube, an elastic recoil is what it's referred to. And as the systolic pressure drops down, 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 and the diastolic pressure right here, again, the aorta is helping to push the blood away from the heart. Because of this, the aorta acts sort of like a shock absorber, and it prevents a shock wave from going from the aortic semilunar valve out to the rest of the body. This dampens that shock wave right there. So over here, just to kind of sum that up, there's an energy surge when the stroke volume comes into the aorta. The wall of the aorta will absorb some of that energy, and then it will recoil and redeliver that energy back into the blood, smoothing out the pulse, keeping it from being such a devastating shock wave. All right. Further away from the heart, you have muscular or distributing arteries. Now, this is the most common to have a name to it, the one most often the names are learned in lab. It goes back to this principle of blood will go, or fluids will go along the path of least resistance. So if there's one inlet right here and 3 outlets, and each one of these things has the same diameter, they're just as open, then this volume X will be split evenly between each one. So it'll be 1/3, 1/3, and 1/3. However, if you restrict one of the tubes in any way whatsoever, what will happen is the flow of the blood will shift to the paths of least resistance. So even though this hasn't been shut off completely, the bulk of the blood will go to the 2 remaining open vessels. So it'd be 1/2 and 1/2. If you were to pinch a second right here, first and the second, then most of the blood would shift to the third, and this would be a complete X in and X out. Again, the path of least resistance. Because of this, it's not necessary to pinch off the blood vessel completely to redirect the blood. All you have to do is make one opening less open. All right, next thing here is arterioles. Arterioles are at the end of the muscular or distributing arteries. These are the smallest arteries, and at this stage right here, the pulse has disappeared or is disappearing. This is barely just an endothelium with a few little straps of smooth muscle wrapped around the endothelium. Now, at this stage right here, the pressure has gone down dramatically. The lumen is very small, and so therefore these little bitty straps of smooth muscle are able to pinch this off. And so there's a great deal of control right here when it comes to where the blood is going to go. The next step is to go into the capillaries. And the capillaries in general are the endothelium of the previous vessel. So therefore we have, complete capillaries, fenestrated capillaries, and sinusoid capillaries. The complete capillaries are basically just a pipe. There are intracellular clefts that white blood cells can move through, and that large objects like proteins might be able to get through, but it's generally complete. The fenestrated capillaries are like the complete, except that the endothelium may have some thin spots in it. And these thin spots or windows are called fenestra. And this allows more material to move through the wall of the capillary. This is particularly abundant in places where hormones are passed back and forth and where there's a great deal of filtering going on. So inside the Bowman's capsule of the nephron in the kidney, there's a lot of fenestrated capillaries. Also in and around endocrine glands, such as in the around the anterior pituitary, a lot of fenestrated capillaries there too. Last type right here is called sinusoid, and the sinusoid is unique in that there isn't a single channel running down the middle of the tube. So there's an entrance and there's an exit, but there may be many different channels to go from this end to that end right there. Because of that, the blood slows down dramatically and has more time to bump into the cells that make up the walls of this area. This is particularly significant in the liver, where the cells inside the wall have the opportunity to modify the chemistry of the blood. This is also a place where macrophages are hiding out and ready to get rid of old red blood cells. So the purpose of this is to slow the blood down enough that you can chemically modify it. Well, beyond the capillaries, you have the venules, and the venules are very porous. And when white blood cells want to get out of the blood, they may use the intercellular clefts found in these areas right here, but they can also use the intracellular clefts that are found inside the venules. The veins are just one step up when it comes to size and volume that they're carrying, and something unique about them is the fact that now we have the possibility of valves. The valves tend to have two cusps. Each cusp sort of looks like a back pocket. They're on opposite sides of the lumen, and when the blood tries to go in the wrong direction, the pockets fill up, bump into each other, and they act as a one-way valve. Now, these valves are very helpful because the push of the blood going from the systemic capillaries back towards the right side of the heart is fairly insufficient. The left ventricle doesn't create enough pressure to be able to push the blood to your extremities around the corner of the capillaries and back towards your heart. So you have to have some other mechanisms to allow any increase in pressure to be taken advantage of. And that's what these valves allow inside the veins. Any increase in pressure below a valve will push the blood up. When the blood tries to drop back down again, the valves will close off. And this way, you can literally step up one valve at a time back towards the heart. These valves, again, being extremely important in helping the blood get back to the right side of the heart. An insufficient valve right here could lead to varicose veins and other problems. Finally, as we get closest to the heart, we have Vena Cava. And as we get close to the Vena Cava, we notice that the lumen is now becoming particularly large. And because of this, something called laminar flow becomes possible. Laminar flow refers to the idea that when fluids are moving through a pipe, the fluid nearest the wall has the greatest amount of friction or resistance and thereby slows down. But the fluid towards the middle of the pipe has less resistance and therefore can speed up. Because of this, when we looked at the speed of the venous blood, we said, okay, blood went from 40 centimeters per second down to 0.1 centimeters per second, and then it sped up a little bit. Even though the pressure was going down, the speed went up a little bit. Here's the reasoning right there, laminar flow. As the vena cava get larger, the blood in the middle has less resistance and can move quicker.